Precompression, flanged beams, and tendon arrangement. Precompression is an important item when it comes to post-tensioning. Some of the ACI design requirements and tendon arrangements are based on the understanding of precompression. And the focus of this presentation is to shed light on this understanding and make or suggest improvements in the understanding which will make it more rational when it comes to treatment of precompression. I start by distribution of precompression in the member, then move to flanged beams, effective width which is associated to flanged beams, then evaluate the compression, precompression, the way the code understands, because the arrangement of rebar and tendons in some instances is based on the code ACI understands and calculates precompression. Then I will discuss about beam modeling and judicious application of tendons, reasonable application of tendons in the members. Let us start with flanged beams and effective width. Effective width concept used in post-tensioned members is the legacy of an old simplified method to design or see flanged beams in bending, which is overtaken to post-tensioning. With today's engineering knowledge and understanding, the traditional method is neither correct nor necessary. Specifically, it doesn't apply to post-tensioning. I want to repeat this, doesn't apply to post-tensioning, the traditional scheme. It is on top of requiring additional design work to arrive at less accurate designs. We do more work in order, and then as a result, we end up with a less realistic solutions. In the following, we review the background to the introduction of effective width. Next, we cover the question of why it doesn't apply to post-tensioning. Now let us concentrate on the background. The distribution of axial stresses from moment in the flange of a flanged beam is shown in A and B here. This is simply supported beam under uniform load. There is a bending moment. The distribution of stress in the flange of this beam is as shown in magenta. This is the real distribution. It is higher at the connection of the stem to the flange, and it tapers as shown there. When simple beam formula is used, the simple beam formula is shown at the bottom right. It says stress is equal to moment divided by moment of inertia times distance. This formula assumes that at distance c from the centroid, the stress is uniform, not tapered. So when flange beam formula D is used to determine the maximum stress at flange stem the connection, the tapered compression in the flange is substituted by a rectangle of equal area to the tapered distribution as shown in the figure C. Here, this area, the blue, is equal to the magenta behind it. So the traditional work assumes a distance such that the area below the rectangle will be equal to the actual stress distribution. This, along with the formula shown at the bottom right, will give us a stress which is reasonably realistic for the connection between the flange and the stem. The width of the substitute rectangle, this substitute rectangle C, is defined as the effective width for bending when simple beam formula shown here is used. The axial stresses in post-tensioned tapered beams are combination of actions from bending and pre-stressing. Now, coming to post-tensioning, the story is a little bit different because the stress is a combination from two sources, not like in pure bending. When you have post-tensioning, the stress is from bending and axial. We have two sources. The effective width for bending doesn't apply to pre-stressing since stress distributions are widely different. So this scenario doesn't apply to post-tensioning. Why it doesn't apply to post-tensioning? Because in post-tensioning, the distribution of the stress is not tapered as it is in bending. For pre-stressing, a different effective width applies. The following explains. Now, I am going to concentrate in the next one or two slides on what is the effective width for post-tensioning. For bending, it is something like what I have shown here. Now, let's bring this here. The example that I'm giving here is intended to serve as background to the effective width concept of flange beams that follows next. So this example is providing you with the background. Figure A shown here, in this figure A is the section of a member with irregular geometry. Here, this is a member, its cross-section shown in A. Purposely, I have selected an irregular cross-section. B, here, shows the elevation of the member with this irregular cross-section. The distribution of stress F here the distribution of stress F away from the point of application of P. This is away from this point. Here it is away from this point, is uniform axial. Since P acts at the centroid. If P is acting at the centroid, the definition of centroid is that it will end up with uniform stress here. If force acts at the centroid, the outcome of it will be uniform distribution of stress over the entire cross-section, not the tapered we have in bending. If P is off center, if P doesn't act on the center, as it is shown here, then it can be broken down into a moment, because it is off center, and axial. Now, the bending component would be subject to effective width. This bending component, like the previous slides, will have an effective width concept applied to it. But the axial will be uniform. The axial of it will be uniform. Bending will be subject to effective width. This concludes that irrespective of cross-sectional geometry, irrespective of the shape of the cross-section, and irrespective of the point of application of the force, there will be a uniform distribution of precompression away from the point of action, independent from the bending effects. When I say uniform, that is for the axial for the force at centroid, and then bending is to take account for the eccentric action of the force. Now let us look at this flanged beam I have shown on the top right. A post-tensioned flanged beam shown in A is subject to bending and axial stresses. For computation of stresses in the flange from previous pages, the bending moment is modeled using an effective width shown in B. If the tendons are not anchored at centroid, there will be a bending because of eccentricity, and the bending will have some distribution of axial stress which is non-uniform, more at the connection to the stem and less as you go farther away. So there will be non-uniform distribution, and the effective width would apply. As shown here, the green is intended to show the effective width, and the distribution is shown here. The axial component, irrespective of the point of action of the axial force and the geometry of the flanged beam, will result in a uniform precompression over the entire section shown in C, away from the point of application of the force. Now, this is showing the distribution of axial from post-tensioning. Observe that the axial is uniform. It doesn't matter where the tendon is anchored. Often the tendon is anchored off center, but the axial is uniform. The two images illustrate that for bending you have a given effective width, you do not have that for axial. Figure A here shows at the top right, shows a typical two-span post-tensioned beam and one-way slab construction. Both figures show the distribution of axial precompression from the tendons that are anchored at the beam ends. The distribution of axial is uniform when you are far away from the point application. At the point of application, there will be some distance for the compression to disperse, and it disperses uniform. Here shows the dispersion, the little wedge-shaped area where the stress is less, but otherwise away from the point of application you have a uniform precompression as shown here. The distribution of axial stress away from the ends of the member is uniform, as shown here. The uniform distribution does not depend on the point of application of the tendon at the beam ends. Doesn't matter where you anchor. I have shown here flanged beam in the manner that simple engineering models the beam and slab for design. If you have a software that models the entire as shown here, you do not go through this routine that I am going to describe. What is being described is based on the assumption that you will extract from the construction a typical representative element which consists of a beam stem along with an associated flange. Now, there you need to know how much of the flange you are going to consider to act with the stem. So the tributaries for axial and bending effects are shown here. In the design of a flange beam, where a single stem and the associated tributary are extracted for the analysis and design of the structure, the treatment of the section for computation of ACI, the computation based on ACI is shown in figures A and B. For the axial force, from post-tensioning, the selection shown in A applies. For axial force, you take the tributary, and then the next one will have its own tributary. The stresses from bending act on a reduced selection. For bending, you take a reduced width. If you use computer programs some computer programs in the market recognize this. Even if you give the tributary in the background, the software for bending takes the narrower and for axial takes the entire. So it depends on the software you use. So coming back to precompression, I'm going to bring some examples. Look at the flanged beam shown in A top right. The post-tensioning applied here is constant, but it is off-center. This is off-center. Well, flange beam shown in A. The post-tensioning force is constant. Tendon is straight. In this case, sorry, the tendon is at centroid. The tendon is centroid and straight. The cross-section is A. The question is, what is the distribution of precompression at midspan? Tendon is at centroid. Tendon is straight. What is the precompression at midspan? What is its magnitude? What is its shape? What is its magnitude? The answer, precompression is uniform over the cross-section. Its magnitude is force divided by A. Force divided by A. Why are we dwelling so much on the precompression, magnitude of precompression, distribution of precompression? Because ACI uses precompression as an important parameter in design of post-tension members. So precompression is a component which is used. So we want to better understand it and know its magnitude. And going back again to value of precompression, the figure A is a flanged beam, single span, eccentric tendon, and profiled. It is with eccentricity and profile in both instances, one span, two span. The question is, what is the distribution and maximum and the value of precompression at midspan? What is the distribution and magnitude of precompression at midspan? The answer, in all cases, precompression away from the point of delivery of post-tensioning, namely at midspan in this case, is uniform distribution over the section. The answer is, for these two arrangements, both have the same precompression in distribution and in magnitude. The magnitude of the precompression is tendon force divided by the cross-sectional area. Looking at it one more time, the precompression in elevation is uniform at midspan. Looking from the top is also uniform. This is applicable to single span, is applicable to continuous, whether the tendon is axial, anchored at the centroid or off-center. In this case, I have shown it off-center. So, when it comes to modeling, beam modeling for analysis and design, if you have a slab and a beam, the actual arrangement of the beam could be something like one of the three conditions: downturned, upturned, or something like this, which is partly up or down. The most analysis software, commercial programs, computer programs, using finite elements internally. Model the beam as shown here, bottom, but display it in the output as shown here. On the screen, this is what you see, but in reality, in the background, this is what the program does. I might have an example here. Let me see, which will show how you can verify this for the program that you use. Now let us move this out of the way. The approximation can be tolerated. This approximation can be tolerated in RC, reinforced concrete, and be safe. That means your design could be safe if this is what you assume and you have conventionally reinforced concrete, but not in post-tensioning. For post-tensioned members, the eccentricity of tendon is a critical component in its contribution in bending. Hence, the analysis model needs to be faithful as shown below. In post-tensioning, the position of tendon will have eccentricity, and that eccentricity gives you the bending moment. But if you change the position of eccentricity, you disregard it in the model for simplicity, obviously you do not get the full benefit of post-tensioning. The modeling of beam integrated with the slab for analysis in the configuration shown here leads to complex formulation. If you want to model the slab and beam as I have shown here, your formulation would be complex because the centroid is here and the centroid is there, and for handshake of the force at the centroid of the stem to the centroid of the flange, you have to come up with an additional formulation, and that is what is missing in most software that is in the market right now, at least. So what is the proper approximation? When a flanged beam is modeled as an integrated entity shown in A, the solution of the beam shown includes a tension force T. Now that is interesting. That is interesting. If this is the way it is modeled, I like you to observe that there is compression here in the flange, there's tension in the beam. And if for design you select the stem and bring it out, the stem has a bending moment and has an axial tension. So if in the software that you use, when it comes to the design of the beam extracted from an arrangement shown on the left, you must have tension. If the software doesn't give tension in addition to bending, it means that in the background, the software did not model the geometry as shown here on the left. It modeled it by putting the stem centered on the flange. That is the diagram that shows the condition more clearly. The precompression that is in the flange must be balanced by a tension in the stem. When in the analysis model the beam is not integrated with the flange, the solution reports zero axial. But you have to have a tension if it is done right. For post-tensioned flanged beam, the modeling shown in B is not proper. This is not the right model. That means if you cut it here, no, this is not the right. This is not the right model if there is a joint. Now, next is a judicious application of PT tendons. What do I mean? Unlike rebar, post-tensioning is an applied force. Hence, it matters where it acts. Rebar could be anywhere. It is not harmful, but post-tensioning can be harmful if not positioned at the right location. I have an example here to illustrate. Figure A shows a simply supported beam. The beam is designed once as RC and once as PT. I designed it once as reinforced, conventionally reinforced concrete, and once at RC. Here in the diagram, I come up with two bars required by design, but I add the same two bars at the top also. So what I have done, I have the design as required to resist the load, but I have in addition put the same amount of reinforcement on the other side. Then the required reinforcement in each case is shown in the left of the figure. This is required. The left figure, if it is conventionally reinforced, and this one is post-tensioned. It requires 4 strands. No. In each case, reinforcement is added beyond what is required by design, as shown in parts of figures C and D. Here, 2 bars were required. I have added additional 2 bars on the top. 4 strands were required at the bottom. I have added 4 strands on the top. So I have added rebar or post-tensioning were not required by design. Now, the impact of extra reinforcement at top of the beam is reported in the next session. This is the elevation, added rebar or added PT on the top bar. The comparison between the performance of the 2 cases shows slight improvement when rebar is added, but loss in performance when PT is added. Now, in the conventional reinforcement condition shown here, the diagram on the left is by design. The diagram on the right has the added rebar. For safety of the member, the one with added bar slightly improves the capacity because it improves the compression zone. For cracking, slightly improves because gives the member added stiffness. For deflection, slightly improves. Deflection will be improved because the member is stiffer. What I conclude is if you add rebar at a location that is not required by minimum design specifications, you do not hurt the performance of the member. It will improve slightly in certain respects. So it is okay for rebar. When it comes to post-tensioning, the one on the left at the bottom left is by design. The one on the right has added tendon on the top that was not required by design. When it comes to safety, we see that it reduces the capacity of the member. Why does it reduces the capacity of the member? Because in the compression zone, you have introduced some tensile force, which takes away from the concrete compression that can be developed there. When it comes to cracking, it is worse. It cracks sooner at the bottom because the strands at the top apply a moment which counteracts the which is additive to the moment from self-weight, so it will result in earlier cracking. And deflection obviously will be more. Deflection will be more because you're adding moment in a direction that induces greater deflection. So A and B show typical flanged beams. A and B, typical flanged beams. The tendons shown in the flange will be in the compression zone. Here, the tendons are in the compression zone, in addition to the tendon here. Tendons in the compression zone of the member are detrimental. I want to emphasize the word detrimental to the member's strength and safety. They reduce the bending strength of the member. The practice is promoted by the industry. This practice is promoted by the industry to put tendons in the flange under the pretext of temperature tendons, since its application increases the amount of post-tensioning in the member. Now, I want to emphasize this. Why industry promotes this application? Because the application increases the usage of post-tensioning. It is beneficial to those who supply post-tensioning to strand makers. So industry is not willing to support a practice that is not favorable to their pocketbook. Here, figure C and D illustrate a failure mode of flanged beams with tendons in the compression zone. Unlike added rebar, the temperature tendon outline adds cost to the construction, while it weakens the performance. It adds cost. In this case, we charge our clients more to deliver less. Now, I have here the plan view of flanged beams, stem on the left, stem on the right. The view here shows the flange, and we have tendons in the flange. Example of straight tendons and in mid depth between the stems, a practice that leads to reduction in members' strength. These are harmful for flange beams. Now above shows the same practice for flat slab. For flat slab, they are not harmful, but they are not beneficial either. It is just a waste of material. So temperature tendons between the bands in a flat slab construction is a wasteful practice. Here on the top shows the practice for unbonded tendons, and the bottom right shows the practice for grouted tendons. ACI 318 and now also 320. This is an advertisement from 318. In this beam example here, there's a beam example for the load applied from the top of the member, as is the common application. In the common application, the load comes from the top. Where the beam is horizontal, load is vertical. The post-tensioning in the flange will help to break the beam in two. The post-tensioning shown in the flange actually helps to break the beam. Removing the tendons in the flange improves the safety of the member. The above comment does not apply if the member shown in the image is intended to be used as a column. Yeah, if this member is used as a column, it is okay, but not if it is used as a member. Then why is it practiced? Very simple. Because industry benefits from it, not the owner. It is for the benefit of the industry. They can use more tendons and the profits will be more. So in summary, flange beams effective width. I went over the definition of effective beams, talked about definition of precompression and its distribution, talked about effective width for precompression. Precompression, I repeat one more time, the way it is in reality and the way the code defines it. The code defines it based on intuition and practice of our former contractors, but its value is, as I showed, uniform in most instances. I talked about beam modeling, how it can be modeled either attached to the, in the modeling attached to the flange or not. Most computer software available for purchase on the screen show the stem attached to the flange, but in the background they model it detached. And then I talk about judicious application of tendons, emphasizing that put tendons where it is beneficial, not when it is harmful. The material was extracted mostly from the book that is shown here. Thank you for listening.